Hi, welcome to a new video. In this lecture, we're going to discuss box-Jenkins methods. This is part one. In part one, we will focus on autoregressive models and moving average. Okay, so in this session, we're going to cover first how to identify if a time series is stationary. Then we will discuss autoregressive models. Of course, in order to identify these models, we need a brief discussion in autocorrelation functions and the partial autocorrelation function. Okay, so let's get started with the Box-Jenkins workflow. So the first step, every time you're going to analyze a time series, you need to plot the original time series. So you can see whether it's stationary or not. However, it's better to perform some tests, like to really confirm from a statistical point of view that our time series is stationary or not, so we can proceed. And the Box-Jenkins methodologies, they use the ACF and PACF that we will see in the next slide. And these are really important to understand the structure of our time series. And the idea is to use previous values of the time series to predict new values or values in the future. So these models, they will have some parameters. So the autoregressive model, AR, will have the parameter P. The moving average, or MA, will have parameter Q. And later, in our next lecture, once we use ARIMA models, we will also include D into our analysis. Okay, so once we have defined which model we want to try, we need to estimate the model parameters. We will fit them with maximum likelihood estimation. In this specific case, we will be using Python, but of course you can use R as an alternative to all the estimation. Once you have trained your model, then we need to check the residuals to see that everything is independent, that there are no correlation the residuals, that they are just white noise. So for that, we will discuss the John box test, and also we will be using ACF and PACF to check that our residuals are independent. And finally, you will be able to make forecasts. We will use the models to predict. Okay, so a key reminder here is not just for time series, this is also in machine learning in general. Typically, we refer to parsimony, which means that in general, we want to find good models, but minimizing the error is not the only goal. We also want to find like the simplest possible model, right? So because sometimes you can get a very complex model, maybe it can overfit your data. So parsimony means trying to find a good model, but that is simple. Okay, so let's talk about what is autocorrelation function and the partial autocorrelation function. So at this point, I'm sure that most of you that are watching this video, you are familiar with what is correlation. So typically we measure like linear correlation when we have two variables and we want to check, like if they are related or not, if one increases or increases, if one decreases, the other increases. So you want to measure like what type of correlation they have. That applies for numerical variables and even for categorical variables, you can measure association. Now, when you talk about autocorrelation, this means you want to find the correlation between the variable and the variable itself. It's like with the same variable. So maybe you're thinking, okay, if I do that, I will get a one, right? Which is true. If you check the autocorrelation function, the ACF here, the plot, when the lag is zero, and I will describe it soon what is the lag. If it's zero, that means that you compute the correlation of the data with the same data, so it is equal to one. That's expected. That's expected, right? Now, so what we do here to make it interesting is that remember that in Box-Jenkins, you identify whether the structure of the time series, like previous values, can be used to predict future values. So when we talk about the lag means previous values. So if I say lag equal to 1, it means that I'm going to measure the correlation of the time series, like the original values, with one value right before or just before the observation. For example, I want to compare month 2 with month 1, month 3 with month 2, month 4 with month 3. So we keep going. So that's our correlation with lag equal to 1. So lag equal to 5 means I'm going to check the correlation with 5 values or 5 periods before, like t-5, right? That's pretty much the idea. So the lag gives you, it's going to help you to evaluate the correlation or the autocorrelation with previous values to identify if there is a structure. Now, why we have two functions or two plots here, the ACF and the partial autocorrelation function. And in this plot, you can see that, for example, in the ACF, let's see that here, like 1, there is a strong correlation, which it shows because if you see the shaded area, and the shaded area means that the correlation is equal to 0. So everything that is inside the area means equal to 0, right? Same here in the PACF, it's equal to 0. So now we're interested in those correlations or autocorrelations that are, like outside that region, right? Because it means that they are different from 0. Now, what happens with the ACF is that if the lag 1 is significant, like in this one, it may affect future values, like other, like the autocorrelation for other lags. So that's why we use the partial autocorrelation, because this one ensures that it measures the direct connection for that specific lag, and that's not going to affect other lags. It means, like, for example, here, when you see the ACF, you see like the effect, like almost until lag 15, right? You see that, there is some effect. But that's because we have strong relationships in the initial lags. Now, if we go to the PACF, we see that there is a strong correlation at 1, lag 2, and lag 3. Even lag 3, I'm not sure it's right in the border, but let's say lag 3. But after that, there are no strong correlations, right? So for that reason, you see in 4, 5, up to 15, you don't see like more relevant autocorrelation values. So that's because the PACF does not get affected by intermediate relationships, which is a problem of the ACF. So this doesn't mean that the PACF is better than the ACF. So it just means that you need both in general. And actually, when we're using AR, MA, ARMA, and ARIMA model, Box Jenkins in general, we will use these two plots or these two methods, if you want to say it like that, to identify which model we're going to use. Okay, so it's really important during the first step to check whether our data or our time series is stationary or not. So a very common test is DQ or augmented DQ. You will find it again in it's popular. You will find it in Python, same thing in R. The null hypothesis is that the series is non-stationary. That's the null hypothesis. And of course, the alternative hypothesis is that the series is stationary. So once we perform the Dickey-Fuller test and we get the p-value, so if the p-value is smaller than alpha, which typically is 0.05 or 5%, then we reject it, well, the hypothesis is small, and we claim that the series is stationary. So in order to claim that our time series is stationary, the p-value has to be less or smaller than 0.05, smaller than alpha in general. So that's like the key thing to remember when you perform the Dickey-Fuller. The null hypothesis is that the time series is non-stationary. That's the null hypothesis. So we need to reject it in order to claim that it is stationary. All right. So let's go to the models. The autoregressive model. So when you see regressive, it sounds like regression. It is like a regression, but the difference here is like it sounds like auto-regressive, like with the time series itself. Typically, when you perform a regression analysis, we try to predict an output using, independent variables, so like different variables, x1 up to xk. But in this case, in the autoregressive, we're using the same time series. The key idea here is that we're going to use previous values. So this is how the model looks, the autoregressive model. So pretty much the whole idea is that we want to predict future values of the time series using previous values. This is t-1. It means the observation in the previous period, yt-2, yt-3. Now, how many values we're going to consider from the past? So that's given by this parameter p, which we call the order. That's why you see ARP, that's the order of the model. So if you have AR, let's say 1, it means that we're going to use only one value to predict the next one. We're going to use the previous period to make a prediction of the next one. If we're using AR2, it means that we're going to use the last two values, like t minus 1 and t minus 2, to make a prediction of the next value, right? So you can keep increasing p, but of course that will increase the complexity of your model. Okay, now the challenging part here when we use autoregressive or the next model, which is a moving average, is that just by looking at the original time series, it's difficult to identify which one you should use. It's not that simple. For example, in this problem here, so we have our time series. It looks stationary, right? Maybe there are some regions where it goes below a level and then goes above, but in general, it remains, at a constant level. However, you need to perform a leaky filter test to verify, like to confirm that if it is stationary or not. All right, so once you have done that and confirmed that, then we create the ACF and the PACF, the autocorrelation function and the partial, right? So the typical behavior in an autoregressive model is that the ACF decays. It means that the autocorrelation, they go to zero, or they tend to go to zero. So you see here, it's decreasing. Now sometimes it oscillates, so it will go to negative values, but it keeps going towards zero. So that's a normal behavior too. It's not, they don't have to be always positive. They can be some negative values here. But again, the idea here is the pattern. It's a decreasing pattern. It decays, right? And of course, and this is important because when we deal with real data, sometimes it's messy. Sometimes maybe there is one value here that it's the same level or a bit higher, but then it keeps decreasing. So just for one value, you cannot judge that. You have to capture the pattern in your analysis. So this is not like exact math. These are just more like guidelines to give you an idea on how to handle the situation. But again, this is not like perfect and very exact math in terms of these guidelines. Okay, so the patterns of autoregressive models is like the ACF tails off or decays, as in this one, and then I will identify P, or how many periods I'm going to consider from the past in the PACF. So how do we do that? So we need to check how many, like which values are outside the zero zone, like which values are, which autocorrelations are significant. So of course, in the zero value always is equal to 1, so you always be careful, because depending of if you're working in R or Python, or even depending on the library, in some libraries, the PACF will begin in 1, in others it will begin at 0. So 0 is always equal to 1, ACF and PACF, so it's not included. But here, at like equal to 1, this one is like equal to 1, you see that this autocorrelation is significant, right? It's almost 0.75, and it's smaller than that. So it means that the previous value, t minus 1, yt minus 1, is relevant to predict the next value. So how do I know that I can use a autoregressive model? First, my time series is stationary. Second, the ACF is going towards 0. And then in the PACF, I see where, where it's cutting the significance area. This value is spiking here. Now, it is possible, this is not the only one, maybe in a different problem, okay, like 1 is significant, like 2 can be also significant, but let's say like 3 is not significant. So in this case, that will mean that the two previous values are significant, so instead of using p equal to 1, I will pick p equal to 2. Now if I have a third value, that will be p equal to 3, right? So I will consider 3 previous values to make a prediction. So again, it's important to see that the ACF decays. Okay, in the case of the moving average, so in the moving average, the model structure changes. Please notice that in the autoregressive, we use previous values of the series, like yt minus 1, yt minus 2, up to yt minus p, right? Same values of the series. But in the moving average, we don't use previous values of this series. We use previous values of the errors. So we use previous errors or residuals to make a predict. It's a different model. It's a different model, the moving average. Now in the MA, we don't use P anymore. We use Q here, and the notation matters. But the idea is pretty much the same. It's how many periods from the past I'm going to consider. So it's Q equal to 1. It means we're going to use the residual of the previous period. If our Q is equal to 2, so we're going to use the residuals of the last two periods. Same as I just said in the previous example, it's difficult just by looking at the original time series to identify if I need autoregressive or moving average. So how do we decide that? We need to check our ACF and PACF. Now, the interpretation changes now because in the MA, it will occur when the PACF, when the PACF is going towards zero, it's decaying, this one, it decays. Remember that in the autoregressive model was the opposite, was the ACF, but here is the PACF. And now we will find Q in the ACF. So I will check which value is significant, which autocorrelation is different than zero. So it's outside the shaded area. So in this case, we see a lag 1. It's happening, right? So that means that Q is equal to 1. So in this case, I will try model MA 1. Now, same idea as I just said in the previous one. Let's say that the second one is also important. It's like, significant, different than zero. So if that happens, then I will use MA equal to 2, or meaning that I'm going to use the residuals from the last two periods. The residual from T minus 1 and the residual from T minus 2, right? So this is how the model looks. And of course, this parameter theta, in this case, these are coefficients that multiply the residuals. Same idea in the autoregressive. We get 5 here, 5, 1 up to 5p. These are the parameters of the model that multiply the previous values in the series. There is always an error that's very common in like in general in our models. We use errors, and we try those errors, and we want them to be like white noise. Meaning just like a random observations with no patterns, no autocorrelations, with mean equal to 0. So that's what we want to get always at the end when we get the residuals. Okay, so we have again here two different models, autoregressive and the moving average. So when we're going to pick one or the other, we need to check at the ACF and PACF. So when the ACF decays, then we check the PACF, right? And the PACF, we identify lag P, which is the lag where we're getting on a correlation that is significant. The maximum value here will define P. Like in which lag is occurring then that will give us an idea for P. In the case of the moving average, the PACF is the one that decays, and we're going to find Q in the ACF. Okay, so once we have identified the model, we have trained the model, let me tell you something. It's very common that just by looking at the plots, you don't know like for sure like which model you're gonna pick. That's very common. So don't be afraid to compare models. So maybe you say that, okay, I think maybe I'm gonna try also like not just the MA1, I wanna try also the MA2, because sometimes let's say that one autocorrelation is right on the border, so you can test that. So the key idea here is that you need to have a lot of candidates, that's common, but you need to compare those candidates for the model selection. So typically there are two metrics that we use here in this context in Box Jenkins, and these are the AIC and the BIC. The AIC metric, which is not just used for time series, you will find it in machine learning in general. AIC and BIC are common metrics. So the AIC is the archaic information criterion. The BIC is the Bayesian information criterion. So what is important and things that you should remember is that you want to minimize these metrics. So if you're comparing models, So the one that has the lowest value, the smallest value, that will be the best model, from the options that you have. So you want to minimize AIC and BIC. The challenge here is that they don't have like there's not like a ceiling for AIC and BIC. So it will change depending on the problem. So it's not like an R squared where you know that, okay, it's between 0 and 1. No, in this case, AIC and BIC can be positive, negative. But what is not going to change is the interpretation. The lowest, the better. So we want to minimize AIC and BIC. Now, they look similar. If you check the equations, they look similar. So they have one term. The first term is for the likelihood. So we want to maximize the likelihood. This is good to maximize this. However, it has a negative sign. That's because we want to minimize the AIC, right? So I want this value large, the L, but since I want to maximize that, but it has a negative sign. It means that so the bigger it is, then it's going to the negative side, and which of course is good for the AIC because you want to minimize the AIC. So the first one again, this the first term is how good is the model, but the negative sign it's the opposite, right? So then we don't just check errors here, we also check the complexity of the model. So the second component of this matrix include K. K means the number of parameters. So for autoregressive and moving average, if you increase P and Q, the order of the model, then you're going to increase K. You're going to increase the model parameters, the number of parameters. So we want to minimize that because we want less complexity. Remember the parsimony principle. So the less complex, the better. And of course, we want a good balance with performance. Okay? So again, it's very common to have different models, candidates, and we will pick the lowest AIC or BIC. And for the residuals, for the errors, and after this we're going to see a couple of examples. For the errors, we can use ACF and PACF. We want errors to be independent. You don't want to see correlation or correlation. So the ACF and PACF, they are good to test that. But there are also some tests. One very popular test in the time series context is the Young box, this one, where the null hypothesis is that residuals are white noise or that there is no autocorrelation, meaning that they are independent. So if we do not reject the null hypothesis, that's good. That means that we comply, with our placebo being independent. And of course, you want to check normality with QQ plots or maybe with a specific statistical test. Okay, let's go to examples. Okay, this is the first one. In the first problem, we have monthly retail sales growth. So this is how it looks. This is just the growth. It looks stationary, right? It looks stationary. It's moving around a level. However, remember, we need to verify that. So if we want to do that, we need to check Dickey-Fuller, right? Dickey-Fuller. So this is the Dickey-Fuller test here, and we're getting a p-value of 0.0004. Remember that in Dickey-Fuller, the null hypothesis is the time series is non-stationary. Since the p-value is small here, less than 0.05, smaller than alpha, then we reject the null hypothesis that the time series is non-stationary. Since we rejected the null hypothesis, then we can claim that with a confidence level of 95%, our time series is stationary. So we're good for the moment. Now we create the ACF and PACF. So in Python, you can get that from stat models, I think SciPy also. But here you have the plot ACF, plot PACF, and you get these two plots, right? So you can see that the ACF is going towards 0, right? It's decreasing. In the case of the PACF, it cuts the significant region here in the lag equal to 1. Therefore, I'm going to try, the ACF decays and the PACF, you have this value here, a lag equal to 1. So this is going to define my p equal to 1, because there is only one value within the lag 1 that is significant. Therefore, we're going to try autoregressive with p equal to 1. We're going to use the same method, ARIMA. This ARIMA is from stat models, and we will use it for all models, autoregressive, moving average, ARMA, and ARIMA. In this video and the next one, we will be using the same method. The change here is the order. In the order, the first parameter is P, the second one is D, which we haven't discussed yet, and the third one is Q. So since autoregressive use P, so that's why we have here P equal to 1, but we don't have D and Q for the moment. When we use MA, moving average models, I will change the Q, which is the third parameter here. In our next video, we'll be changing also D. For now, D is equal to 0 because this is stationary. When we have time series that are non-stationary, we also change the D parameter. Okay, so we get our model once we train it, and these are the parameters. This is the constant value of the autoregressive model, and then we have phi1, which is the parameter that multiplies yt minus 1. This is multiplying the previous observation. Okay. Now we can run the diagnostics. From the table that you get here from stats models, you get the Young box right away. The p-value is here, the p-value 0.42, the probability of Q. The Q is the statistics, and the probability of that statistic, that's the p-value, 0.42. So it's greater than alpha. So we do not reject the null hypothesis, meaning that the residuals are independent. There is no correlation. Now we can confirm that, like these are the residuals. You cannot see patterns here. And when you plot the ACF and PACF, you see like most of the values are in the shaded area. There are some in the border. That's common, especially with real data. But when you have issues, if you see some of these lines, going outside the region, clearly going outside, that means that your residuals are not independent, and that's not a good model. You cannot use that model. It's really important. This is really important. Now, the Young box, you can compute the Young box for different lags. So the default here in our table, in the previous table, is lag 1. But now, in general, it's a good practice to have different lags because this is a cumulative value. So if you use lag 10, it will evaluate, the Young box like for or the correlation or autocorrelation, for all lags within like between 0 and 10. So typically you have this for to measure the effect of values that are close to the future. You have for intermediate values that you use lag 15 or lag 20 to check values that are like far from the prediction. In all cases, you see that the p-value is greater than alpha, meaning that they are independent. So this is just confirming that our residuals are fine. So here our model is good. It has like at the end you just get random error, which is good. If you have correlation or autocorrelation in your receiver, that's bad. That means that your model is just capturing all the patterns. Okay, and finally, for this model, you can make prediction, get forecast. You just have to say how many steps, that's h, like how many values in the future, and you can, of course, analyze those values. You see there is like a confidence interval here for the prediction. Okay, let's check the second example. So this is for a pill. Imagine like a pharmaceutical company analyzing weight deviations. So this is the time series. They check first if it's stationary, so p-value tends to 0. Therefore, it's stationary. We reject the null hypothesis that is non-stationary. So it is stationary. So we proceed with ACF and PACF. And now here, the PACF tends to 0. So you see that it's oscillating and going towards 0, right? So it's clear in this one. And then in the ACF, we find Q. Like we need to check which is the latest lag with a significant autocorrelation. It's lag 1. That means that we are going to use the residual from the previous period to predict future values. So here we're going to feed moving average with q equal to 1. So we're going to use only the previous residual. And as I said before, we're using the method ARIMA and the order, which is PDQ. Here P is 0 because this is not an autoregressive model. D, we're not using D. And then Q here is equal to 1. So this is how the functions understand. This is how the ARIMA method understand if you want autoregressive, moving average, ARMA, which is a mix of these two, or ARIMA, which also includes D. Okay, we feed our model, we get the parameters, the constant component, the thetas. This is theta 1 that is multiplying the previous error or previous residual. And we need to run the diagnostics, same idea, Young box, ACF, PACF, to check whether our residuals are independent or if there is some sort of autocorrelation. Okay, we see we plot the residuals, and when you check the ACF and PACF, you see that all values, are in the shaded area. Again, it's normal that with the lag equal to 0, the autocorrelation is always equal to 1. That's for both plots. Okay, so it complies. Therefore, it means that we can use this model. Okay, I'm gonna stop the video for now. I'll see you in the next lecture.